Hello and welcome to episode number 7 of CS350 Online. I'm your host, Leslie, and in today's episode, we are going to finish off our discussion of semaphores and condition variables. And then we're going to look at some of the other sources where race conditions can happen. And finally, we'll close everything off on synchronization by talking about one of the side effects of using synchronization incorrectly, which is deadlock. But first, of course, let's look at the OS of the day. And the OS of the day is one that some of you may have heard of, and that's Multics. Now, Multics was released in 1969, and it's an operating system out of MIT. This operating system here ran on two different series of machines, the G645s and the Honeywells as well. And this operating system is a pretty big deal in history because this is Unix's predecessor. And in fact, some of the individuals responsible for implementing Multics actually went off and implemented Unix. So these two operating systems share many developers. Some interesting things about Multics. So it's the first operating system that ever gave you single level storage. So what they essentially mean by that is they didn't separate file space and address spaces. You could actually access all memory via the file system. And that's kind of an interesting idea because if you look at where Unix took that and the Linux kernel has taken that, it's now you can actually address devices by a file. So for example, if I wanted to send a command or send some data out over my serial port, which I don't actually have a serial port anymore, but let's suppose I did, then I would just write to dev tty0, and I would be sending data over the serial port. So I would be sending data to a device attached to the serial port. And that's kind of a neat way of doing it, right? Because you can treat devices and ports as files. And that all kind of comes back to Multics. They also had the ability to do dynamic linking, so you could access data and code outside of your own address space. So that's kind of the idea of having like dynamically linked libraries. And one of the kind of quirks of Multics is they wanted you to have the ability to kind of reconfigure the hardware of the computer while the computer was operating. So they didn't want you to have to shut down the computer, which could be a lengthy process, and then reboot the computer afterward, which again could be a lengthy process. They wanted you to be able to actually do some configuration while it was still up. And one of those things, now I know, removal of the CPU, that really only works if you have multiple CPUs. And you might be thinking, okay, so we open up the box and we pull out the chip. No, it's like moving fridges around in the gymnasium, like giant things, big things, not little chips being moved around on boards. But this would be things like plugging in extra I/O devices, reconfiguring things like that. And they wanted really to make sure that you didn't have to restart the OS. So in a way, this is actually where the concept of plug and play came from, because they want the goal of plug and play, of course, is that you plug it in and it just works. I just actually got an external webcam for my daughter's laptop because she's doing this whole video school from home. And I didn't install anything. I plugged it in and it just works. And that's great. But people started building that functionality back in 1969. So it's not exactly new. And one of the other big things that Multics brought to the table was the fact that they recognized that security could be an issue and that not every user in the system should have the same access rights and permissions as every other user and their user programs. So they kind of developed security in this ring kind of way, where the further away you were from the kernel, the less and less privileges and access rights you actually had. So if you were the administrator, you could do anything, and then if you were the user on the edge, you could do almost nothing. I mean, you could execute programs, but you couldn't actually access underlying systems directly. And I mean, they had more things to talk about. They had hierarchical file systems, they had per process stacks, they had command processors as a user application instead of part of the kernel. They had many, many different things that they introduced in Multics, and Multics remained in use for many, many years, and I'm sure if we go out there, we can still find people who are using it. And I actually think it's still around. Obviously, I'm not using Multics, but kind of fun. All right, so where did we leave off last day? So I know it's been like 5 days since our previous episode, but we left off, we were talking about semaphores and condition variables. And just to recap that, remember that a semaphore is used for keeping account of how many resources are actually available. So the idea is that instead of letting just one thread into the critical section, maybe you can let 90 in because there's 90 chairs and it's acceptable for 90 people to enter the room. So with semaphore, you can set its initial counter to whatever value you want, and the idea is as threads arrive, they're going to P the semaphore to try to acquire a resource. If they can't acquire a resource because there's none available, then they're going to go to sleep and wait for one to arrive. And if they can acquire it, we'll decrement the semaphore's internal counter. Likewise, when you produce a resource or you release a resource, you're going to V the semaphore, and that's going to increment the counter and wake up one thread that is waiting. So we have semaphores. Now, what was interesting about semaphores, of course, was the fact that you can use them for a variety of different purposes. You can use a semaphore as a lock, keeping in mind that while it can operate as a lock and you can use it to create mutual exclusion, you have to be very careful because semaphores don't keep track of ownership. And if you use the semaphore incorrectly, you will not end up with mutual exclusion. So it's kind of on you to use it properly. And then we have a counting semaphore, which is just a semaphore with an arbitrary number of resources, kind of like for producers and consumers. And then a barrier semaphore, which we kind of use to keep track of once a task is done, and we don't let the calling thread actually continue until the task is completed. And that semaphore usually starts out with a count of 0, and it's going to P the semaphore however many times it needs to, and then it has to wait for that semaphore to be V'd exactly that many times before we can continue. Now, one of the interesting things is that with semaphores, you might think that you have access to the count, but you don't. And even if it's, C code and it's not technically hidden, you really shouldn't be accessing the count directly because the counter needs to be protected by the spin lock, and it just wouldn't be safe for you to directly access or modify that counter inside the semaphore. So you should consider all of the fields of the semaphore and all of the fields of the lock to be private to that structure and only accessible within its actual API. Now, we showed you producers and consumers using a semaphore, and we showed you some of the details of the implementation. I'm not going to review that. Then we introduced this concept called condition variables. Now, condition variables are kind of an interesting story. If you're Googling this because, you want more information or you're bored or you're struggling to implement them for assignment 1, one of the things I want to say is that the condition variables, there's different kinds, and they sometimes go by different names. So we're using what's known as Mesa-style condition variables. So just keep that in mind because there are other styles, and we're not going to cover them here. So the condition variable, the idea, again, just to reiterate what was behind that, is we're inside some critical section, and the lock that is being used to protect a shared variable, so we own it, obviously, because we're in the critical section. And we come up with the problem that the protected variable, the thing we're trying to save from a race condition, has the wrong value, and we can't actually continue. But that's the problem. So if we're waiting for x to equal 5, and x is not currently 5, we can't just set x to equal 5 and continue because maybe the other thread hasn't completed its task yet. So we need a safe way to relinquish hold of that lock and wait for the value of the x to change. And the thing is, the reason why we have to safely relinquish the lock is because the lock protects x. And if we don't relinquish the lock, then the other thread who needs to change x and do some tasks can't acquire x, or can't acquire the lock. So that's what a condition variable does, is it gives us a safe place to wait inside of a critical section while relinquishing the lock so some other thread can change the condition. So there's only 3 functions in the API there, of course, aside from create and destroy. You've got wait, which does the body of the work, and signal and broadcast, which are going to wake one and all threads respectively. Now, wait's a tricky thing because inside of wait, what you're going to want to do is simultaneously release the lock that's passed in and fall asleep. Now, the condition variable should not have any spin locks whatsoever. The only lock that you need is the one that is passed in. And so that's the lock you should be releasing. Now, a lot of people wonder, should I be going to sleep on the lock? And the answer is no. Because if you are waiting on the condition, you're not waiting for the lock to become available. You're waiting on the condition. And those are two separate things. So you have to make sure that when you go to sleep on a wait channel, that you're always going to sleep on the thing that you're actually supposed to be sleeping on. So a wait channel is needed by the condition variable. So you got to simultaneously release that lock that's passed in and fall asleep on the wait channel that belongs to the CV. And then once you wake back up, before you can leave wait, you need to actually reacquire the lock, because when you enter wait and when you leave wait, you need to be protected by that lock. So you need to be offering mutual exclusion. So that's our CVs, and we did some brief pseudocode in our last episode to show you kind of how to implement them, and we also talked about how to test condition variables. There aren't many tests. The test that we recommend you do is SY3, and SY3 is, sorry, the ding, that's my lunch. So SY3 is the test that you have available to you. And I can't reiterate this enough. You can only run one test at a time. So run one test, shut OS 161 down, restart OS 161, and then run another one. You can't run tests back to back because memory doesn't work properly in OS 161. And so as a result, what's going to end up happening is you're going to get some weird errors. Sometimes they're memory errors. Sometimes it's freezing. You just don't know what's going to happen. You can't run tests back to back until assignment 3. And in assignment 3, you're going to fix the problem. But for now, it's not fixed. So don't do it. All right. So that's how you test with SY3. And the other thing I want to reiterate is the fact that you can't just test once. You actually do need to test like 100 or so times. Do that on a single core and then up it to 4. And I don't recommend going straight to 4 because if you go straight to 4, one of the problems that you're going to run into is the fact that if you do have a bug, it's very difficult to debug on a 4-core machine, whereas if you're trying to debug on a single core, that's a lot easier to deal with. So that's why we recommend that. All right, so the last thing that we looked at was, and I'm going to actually go to this in a little bit bigger here. We were looking at an implementation of producers and consumers using condition variables. So just to go over that again, we're going to have our lock. And then we're going to have 2 condition variables because there are 2 conditions. Because the producer is waiting for the buffer to be not full. And the consumer is waiting for the buffer to be not empty. So 2 condition variables because the threads would be waiting on 2 very different conditions. So then in produce and consume looks similar. We're going to acquire the lock. We're going to check our condition. And we do it in a loop here. Because when you signal, there's no guarantee that the thread that you woke up because the condition has changed, there's no guarantee they're going to run right away. It's just like with lock release. There's no guarantee that when you wake up a thread that it's going to start running again and get the lock. There are other threads that may get scheduled before that thread you just woke, and they may end up getting the lock out from under you. Likewise, there are other threads that when you wake them up, they may change the condition back to something bad. So most of the time, but not all of the time, you will see CV wait used within a loop checking the condition. And it is actually, this loop is very much needed here. There is a peculiar way that you can actually use a CV under certain circumstances where the loop is not needed. We're going to do a sample problem with it today, and I'm going to tell you the assignment 1 traffic synchronization problem. Also, you definitely don't want to use your CVs in a while loop. We'll talk about that another time. All right, so we've checked our condition. If it is not, if there's no space in the buffer, then we call CV wait because we're waiting for it to be not full. Otherwise, we add the item to the buffer. We increase the count. By increasing the count, we have changed the condition for the other people, which is the consumers. And so we signal the consumers. And likewise, in consume, we're going to, again, query the mutex. We check a condition, which is different. If the buffer is empty, we're going to wait on non-empty. And when it isn't empty, we take an item, decrement the counter, which just produced an item of space for the producer. So we're going to single not full because the buffer's no longer full. All right. Now, before we go on to volatile here, let's go over to a sample problem. So if you're following along, and go into Piazza, and under the extra sample notes and guides, you'll find an archive of a bunch of extra sample problems. These are actually, by the way, all past midterm problems. And for the record, all of our midterms from midterms past, that long, long time ago where we actually used to show up on campus. All those midterms are actually posted along with their solutions. And these are all questions from previous midterms. So this question here, SEM2CV, gives you a little snippet of code. I'm trying to make it a little bigger here so everyone can see it a bit better in the video, although you can, of course, look at the file online. We have 3 semaphores, A, B, and C. And A and B have been initialized with an initial count of 1 and C 0. And then you can see here in functions 1 and functions 2, which are poorly formatted, but you can see here how we've got these 3 semaphores actually being used. Now, a couple things to know. So what this question is actually asking you is look at the synchronization behavior of this code here, and then keeping the behavior the same, change the semaphores to locks and condition variables. It's an interesting problem, actually. So let's actually look at a possible solution to this. So I'm going to leave that like that. Let's open OneNote. Get out my trusty pen here. Well, I guess you can't see the questions if I have OneNote that big. So let's push that down there just like that. Okay, so first off, if we take a look at function 1 and function 2 and semaphores A and B, we note that semaphore A and B are just being used as a lock. So let's just quickly replace those. So let's I'm going to create 3 locks. And I'm also going to create, for the sake of discussion, because I know in advance I'm going to need a CV. This is pseudocode, and this is pure laziness in naming. And I'm also going to need a counter. Ooh. I'm not sure what that was. All right. So I've got those there. Now what I'm going to do is for function A, or I guess it's function 1, we're going to replace those binary semaphores with just straight up locks. So again, for the sake of time, let's write this very quickly. And then in function 2, we're going to do the same thing. We're going to replace semaphore B with a lock. Okay. Now comes the tricky part. So the tricky part here is trying to figure out what is happening with semaphore C. And what you're seeing is that function 1 P's semaphore C. So it's trying to acquire a resource. And function 2 is responsible for creating the resource. And the number of resources available is 0. So what you're seeing here is that function 1 has to wait until function 2 has run. And each function 1 will have to wait for at least one function 2 to have run. So, how are we going to make this work? Well, this is what the count is going to be. So I've set the count to be 0 because that's the initial count of our semaphore. I'm going to do this in a different color here just to show what we're doing. So what I'm going to do is I'm going to acquire lock C. Because lock C is going to be used to protect the count variable. Now, I'm going to decrement count. I want you to keep in mind, by the way, that there are multiple possible solutions to this problem. This is just one. Now, once I've decremented count, I'm going to check and see if count is less than 0. Because if count is less than 0, then I know that function 2 hasn't run. So what I'm going to do then is I'm going to call CV wait. I am waiting for count to increment by 1. Now, it doesn't necessarily mean that count is going to be like 10. I'm not waiting for count to be greater than 0. I am simply waiting for count to increment by 1. Because I am waiting for an instance of function 2 to run. And then once I wake up, I'm going to release C, my lock. Okay. So then in function 2, what we're going to do is we're also going to acquire C. This one is going to indicate that it's run. It's producing the item. And the first thing I'm going to do is I'm going to check, is anybody waiting? And I know for a fact that if count is less than 0, that I am going to have at least one thread waiting. So since I am function 2, and I know at this point that I have at least one thread waiting, and I'm producing an item, then I should wake the thread up. And I should also increment the count. All right, there we go. So function 1 is going to have to come in. It decrements the counter. If count is now less than 0, then it goes to sleep. And it wakes up when function 2 runs, and it's at the front of the wait channel such that signal wakes it up. Now, a lot of people ask, well, you didn't use this with a while loop. Is there no solution with the while loop? Does this actually work? This does actually work. The reason why this works is because we've kind of done this explicit handoff. You'll note that I am decrementing count before I check the condition. So, let's suppose that the count is equal to 0. And I decrement it to -1 because I am now waiting. And then function 2 runs. It notices that count is -1, so it wakes me up. Then it increments the count back to 0. And then it releases the lock. Let's suppose a third thread comes along and runs before I actually get a chance to run. So it's going to go into function 1 and it's going to acquire the lock and decrement the counter, pushing the count back below 0, meaning that it will then wait, context switch back to me, and I can safely run. So the while loop here, because we've explicitly ordered these things in a way that kind of hands off the counter, we don't need the while loop. But that is exceptionally unusual. That being said, on assignment 1 for your traffic simulation problem, if you are calling CV wait inside of a loop, you are going to have a very bad time. You probably will not pass the computation requirements. So don't do it. There is a way to explicitly hand off the condition such that it blocks every other thread from barging in front of you. Wink, wink, nudge, nudge. Maybe look at a traffic light. That's my hint. All right. There are other solutions to this problem too, by the way, that do use while loops, but there's no need. And I believe, actually, I was looking at the grading scheme for this. If you used a while loop for this, you actually lost like half the marks or something. It was especially cruel, in my opinion. All right. So then, let us go back to synchronization. So there's a question on Twitch here. If you see me turn my head over here, it's because I'm looking at one of my other machines that actually has the Twitch chat open. So since CV signal is a no-op, if there is no waiters, is it possible to simply call CV signal in function 2 without checking for waiters? Yes. You can absolutely do that. There's no problem with that whatsoever. Probably the reason for actually checking here is because in the end it'll work out to be fewer instructions. Because if you think about what CV signal has to do, so that's a function call, that's a whole bunch of loads and restores of registers. So you call CV wait or CV signal, and then inside CV signal you're going to call wchan wake 1, which again is another function call. So that's going to be a whole bunch more loads and saves of registers. That's just going to be a lot of work. And if you look at checking if count is less than 0, even though that is a branch and branches are not exactly free, the number of instructions we would use for that is significantly less than always calling CV signal. Is there a reason why we increment the count after calling CV signal? I actually don't think it matters here. Sometimes it does matter, but I don't think it matters in this one. I'd have to sit there and play with it for a few minutes. All right. I mean, generally speaking, so you want to make sure that when the I want to make sure that other threads aren't going to interfere with things. But in this case, as I said, I don't think it matters. So somebody says, what if we context switch to function 1 before incrementing count? That's actually not possible. So what would end up happening if we go back to one note here? Let's suppose that you context switch in between CV signal and count plus plus. And so let's say, so we would wake up inside of CV wait. But the problem is the very last thing we do before we leave CV wait is we acquire the lock C. But since function 2 hasn't actually released lock C, then our thread in function 1 would actually go back to sleep until function 2 releases the lock. And it can't release the lock until the count is actually incremented. So it's not actually a problem. The reason why, by the way, another Twitch question, why do we decrement before checking? That actually has to do with blocking other threads from barging in the front door. So if we didn't do it in that specific order, then we would probably have to use a while loop to check the condition each time. So you got to be careful about that. If you set the counts or the shared variable in a specific position, it often impacts whether or not you need the while loop. And again, that can't be done with every problem. All right, if there's any more questions about this particular problem, by all means, don't be afraid to ask on Piazza. But I would like to move on to our last topics. All right. So we've spent a lot of time. Okay, one more question then. So on Twitch, someone says, if function 1 is called multiple times before function 2 is called once, does count keep decrementing? Yes, it does. It keeps decrementing. And that's fine, because we are not asking function 1 to wait for the count to be equal to something greater than 0. We are simply saying function 1 has to wait for an instance of function 2 to operate first. So every function 1 must wait for a separate execution of function 2 before it can continue. So we're not actually saying no function 1s can continue until the counter is greater than 0. And that's also why you have to, if you do solve that problem with a loop, you have to be very careful, because it's very easy to cause all of the function 1s to wait for the counter to be greater than 0. Okay, enough of that problem. So we've been talking a lot about the sources of race conditions and how we actually solve the race conditions by putting things in mutual exclusion and by using semaphores and condition variables. The race conditions, however, that we've been solving are all 100% your fault. It's you have written some code without taking into consideration that a context switch can happen at any time, and therefore many of your memory operations aren't actually safe, because some threads may be reading a variable at the same time as another thread writing, and that's just not going to be safe at all. Hence the synchronization primitives, which we can use to actually control how threads execute instructions through certain regions of code. There are, however, other race conditions that can happen that aren't your fault. And one of them, and I said on Piazza and I've said earlier, we would come back to this particular topic, is that of volatile. If you go back through all of these slides, you will notice that all of our shared variables here have been marked as volatile. Volatile there, volatile here, volatile there. Everywhere throughout these slides, you'll see the use of this volatile keyword, but we don't actually explain what volatile is and why you should use it. And if you go onto the internet, you're going to see a lot of interesting discussion and argument over whether or not volatile is necessary. First off, you need to understand what volatile actually does before you can make that decision. But before we get into volatile, let's talk about where those other two sources of race conditions actually come from. One of them, related to volatile, is your compiler. And this is not your fault. And the problem is that the compiler isn't aware that that block of code or that particular variable is going to be accessed by multiple threads at the same time. And so when the compiler is doing any kind of optimizations, it does many things like instruction reorganization, and it does this one called register allocation, where it says, instead of getting that variable's value from memory every time, why don't I store it in register 8 for this period of time? And then I know that register 8 contains the most up-to-date version. Well, that doesn't work if you have multiple threads. If we reorder loads and stores, we could move loads and stores outside of locks, protected areas, and actually end up introducing race conditions when our code was actually written correctly. So your compiler, in its optimization phase, may actually end up adding a race condition to your code. That's not a huge surprise. The one that always surprises people is your CPU does it too, which is the third source of a race condition, your CPU. Your CPU also tries to optimize code. It is able to look ahead, and it is and does reorder instructions to reduce the number of memory operations, or however it can make things cheaper, it will do it. Unfortunately, if we reorganize loads and stores, we can move them outside of their protective barriers, causing a race condition to appear. So these two things are actually a lot newer of a concept because the compilers are a lot better, or compilers have gotten a lot better at optimizing things, and CPUs have gotten much, much, much more complicated and sophisticated. And so they can do a lot of these optimizations. And so we've had to introduce, and I mean, these have been around for a long time, this concept called a memory model, which is really just talking about how do threads access memory in shared regions. So how are we what's the behavior of memory access in a shared region? And the memory model is telling the compiler and the CPU exactly what order those instructions have to be performed in order to have things work out. So first off, and by the way, so memory models, they're not just present in the compiler, they're also present on a CPU. So if you can actually look up Spark's memory model, and it will tell you that, okay, you can expect that the store operation is going to be, if you see this store followed by this store followed by this load, the CPU is going to reorder them in this following way. And so that's telling people, okay, this is how we're going to do it, so that they can plan ahead. We'll talk about how the solution to those works in a minute. But first, I want to talk about some of the compiler's optimizations that cause problems, and in particular, Volatile. So this is actually an optimization in a compiler I know pretty well because I've implemented it. In a commercial compiler, even. And the idea is that we really want to eliminate the number of loads and stores that our assembly is doing, because loads and stores take more than the typical number of cycles. Like, they take longer than an add or a subtract. And I mean, that's why we have to use knobs, right? Because in a pipelined architecture, if you try to use a value immediately after loading it, it's not going to work out because the load takes more cycles than the other operations. And so we actually need to introduce a delay to wait for that to happen. So we actually want to eliminate as many loads and stores as possible. And so this concept of register allocation, we're actually going to look at the code and we're going to try to figure out, okay, can I keep these variables in registers? And for how long can I keep each variable in a register for? So if you look at this little bit of code here, we have two functions that are going to make use of shared total. But here's the problem. Function A, when we're doing the register allocation analysis, we may place shared total in register 3. And so we're going to load at the very beginning of function A, we load shared total into register 3, and then for the entire body of function A, which could be huge, shared total is not in memory, it's in register 3. And then in function B, we load shared total into register 8. And for the entire body of function B, the up-to-date value of shared total should be in register 8. But the compiler doesn't know that function A and function B can actually execute at the same time. And that's actually where the problem comes from. Because if shared total is in register 3 in function A, and shared total is in register 8 in function B, what if those two functions run at the same time? Who has the up-to-date version or correct value of shared total? Probably neither of them. And so there's a race condition that even if you had a lock, oops, race condition still happened. So how do we stop the compiler from doing this? Well, there's a magical keyword you can use to tell the compiler, hey, don't do it. Please do not store the up-to-date value in a register, and please do not reorder the loads and stores with respect to this variable. And that magical keyword is volatile. So if we make a shared variable volatile, we are saying, do not optimize this variable. We are saying every time I need to use this variable, please load it from memory and then immediately store the result back. And please don't reorder the loads and stores. So in your code, it's absolutely imperative that you make all of the shared variables volatile. And you can put the keyword I think there's like 2 different places you can put the keyword, by the way. Now, is that going to eliminate the race condition over shared total? It eliminates the compiler-induced race condition over shared total, but it doesn't solve your race condition. So using Volatile doesn't mean you don't need locks, because the only thing that Volatile does is disable an optimization. Volatile is not a lock. It cannot be used as a lock. It is only disabling an optimization, and that is it. Make sure you use it. Now, if by chance you don't use it, you'll probably be okay, but please still do use it because it'll make debugging easier. And the other thing I want to say is that if you make things volatile that don't need to be volatile, that's actually okay. And the reason for that is because you're just disabling an optimization. So your code has more instructions. It's not as fast. Whatever. Not a big deal. Now, that's really the only language level control that we have in this course, because we're using an ancient C standard. I don't recall if we're using C89 or C99, but it doesn't matter. We don't really have a lot of the other problems associated with multi-threading in C. However, if you look at the latest C standards, they actually have a memory model and language level synchronization. And the reason why they have this language level support for multi-threading and synchronization is because they wanted to make sure that the compiler was aware of critical sections when it was actually compiling and optimizing your code, so that it can make sure not to reorder instructions within things like a function that could be run by multiple threads at the same time. So, and how this usually comes into play is if you look at the newer versions of C, they actually provide atomic instructions. They have like locks and things built in that you will actually use in your code, and that will be signaling to the compiler, hey, this is a shared region. Please do not optimize this code. Leave it exactly as it is written. And then looking, just a quick question here on Twitch. So Volatile is only preventing the compiler from ruining the race condition free code. I mean, the compiler can wreck code that has race conditions in it too. Like, it's the Volatile is disabling an optimization. That's all it's doing, is it's disabling an optimization. That optimization can cause a race condition, even in code that is otherwise perfect. But it can also add race conditions to code that isn't perfect. So use Volatile to disable the optimization. All right. Now, the CPU, as I said, also has the ability to reorder instructions, and it does so in order to improve memory reads and writes and other things. So it also has a memory model to indicate how loads and stores are going to behave through shared regions of code. But then you have to ask, how do I prevent the CPU from reordering instructions in a shared block? Because it is possible that it could take a load and shove it outside your perfectly mutex piece of code. So what you actually have to do, and you don't really have to do anything because this would be built into the compiler, is there are actually barrier or fence instructions actually built into many architectures that will say, hey, right here, you're entering a shared region of code. Cease all instruction reorganization. Execute in exactly the order as specified. And then it would just go dot, 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 dot. And when it reaches the end, it will turn those optimizations back on. So we have these barrier instructions on modern architectures to actually disable and enable those CPU optimizations. Now, do you need to worry about this in this course? No. So if you're in the real world running multi-threaded code, this is something to be aware of. But we're running on a MIPS R3000 CPU, and it doesn't have this. It doesn't do this. We don't need it. We don't need to worry about it. It's simulated. I think the first barrier instruction for Sparks, or this isn't a Spark, for MIPS, came in the R4000, I think. I read the specs for these many years ago, but I think it's the R4000 that the first barrier instructions actually start showing up. We don't have to worry about them. The only one of these concepts you need to worry about is volatile itself. All right. So, one last topic. So you've seen the sources of race conditions, and you've seen how to solve each of those race conditions. And now that we've given you lovely, lovely locks and condition variables and semaphores, you might be thinking that your world is sunny and there's rainbows in the sky and everything is perfect and joyful. Nope. Because you can do bad things with them. And these bad things actually cause big problems. And that big problem is a deadlock. So if you look at this piece of code we actually have here on the screen now, you've got two locks and two functions. Both of these functions want to require both of these locks in order to do their work for whatever reason. It doesn't matter what the reason is. So function A requires lock A, and function A is also going to require lock B. And similarly, function B will require lock B, and then function B will require lock A. But here's where the problem comes in. If thread 1 gets lock A, and then there's a context switch and thread 2 gets lock B, so A has A and B has B, but when we context switch back to A, thread 1, and it tries to get B, it's going to fall asleep waiting for lock B because lock B is owned by thread 2 in function B. So it falls asleep. So we context switch back to the thread running function B, and it then tries to acquire lock A, but lock A is owned by thread 1, who is asleep waiting for lock B, and so function B and thread 2 fall asleep on lock A. And it doesn't matter how loud you scream, these threads will never wake. Ever. Because you can't wake a lock, release it, unless you own it. And the owners are both asleep. This situation is called deadlock. So we've got ourselves into a situation where nobody can ever make any progress ever again. There's also, by the way, a concept of live lock, where the threads aren't asleep, but they are, you could consider them actively spinning, but never actually making any progress. So there's deadlock, but there's also live lock. All right. So how do we stop this from happening? This is one of those things where you might be thinking, well, could I build something into the kernel that says, oh, I see here that this thread has been asleep on this, waiting for this lock for an hour. Should I wake them up? Should I release the lock and wake them up and have them try again? No, you can't do that. And the reason why you can't have the kernel sit there and wake up a thread to try again is because the kernel doesn't know what the thread's code actually is. The kernel doesn't know if that thread is legitimately waiting or illegitimately waiting. Maybe that thread is waiting for me to push one of these other strange buttons on my tablet. I don't know what they do. I'm never going to push them. The only person in my house who is ever going to push those buttons is my kids, who are like, oh, buttons, let's push them. But it would be perfectly fine. Maybe I am legitimately waiting on those buttons to be pushed. How does the kernel know whether the wait is legitimate or not? So this isn't something, it's not to say that you couldn't design something, a system that was somewhat intelligent about how to eliminate the deadlock. It's that to say there are lots of details. What we really want is to write code that doesn't have deadlock. Now, deadlock usually happens in the situation where you are going to need to acquire multiple resources. Now, first off, one of the easiest ways to prevent deadlock is to make the observation that if you're trying to acquire a lock, don't then, after you've acquired the lock, try to acquire the same lock again. Hence why that case cert I mentioned you should put in there, because you should never acquire something you already have. Then there are many strategies that you can implement in your code to do deadlock prevention. We're only going to talk about two of them here. There's also one called the banker's algorithm. which keeps track of how many resources are available in total in the system, how many resources do you currently have allocated, and so on and so forth before it will actually permit you to try to acquire them. But there's two really easy things that you can do in your own code, and this is on you to write correctly. And that is no hold and wait and resource ordering. These are two excellent strategies for preventing deadlock from happening in your code. So how do they work? So the idea behind no hold and wait is you need to acquire multiple resources. But where the problem ends up is that if we can only acquire some of the resources, but not all of them. So what we've decided is with no hold and wait, you are not permitted to own anything while you are waiting to acquire something else. And that can be a busy wait or a sleeping wait. You are not permitted to own any resource while you are waiting to acquire another, which means you must own all of the resources or none of the resources. That simple. I'm going to go over to OneNote here, and I actually want to give you an example of solving that deadlock on the previous slides with no hold and wait. Because it's always good to see an example, right? Okay. Let's get a color and let's do, so we've got function A. Now, no hold and wait says we are not permitted to own anything Sorry, I just heard a funny beep. We're not permitted to own anything while we are attempting to acquire something, which actually means that we need a new implementation of our lock. And in fact, we just need one additional function. And the function we need to implement no hold and wait is called try acquire, which, by the way, we do not have in OS 161, and there's no reason for you to add it. But what try acquire does is it's going to try to acquire the lock. And if it can get the lock without waiting, you get the lock. If you can't get the lock, then instead of going to sleep, we're going to return false. So this is kind of what it looks like. So the first thing we're going to do is acquire. That's a spin acquire. The spin lock inside of the lock. Because we're going to be checking whether the lock is owned or not. If, once we've got that spin lock acquired, if the lock is held, then I don't want to go to sleep. I want to return false. So what I'm going to do is I'm then going to release the spin lock. And return false. Okay. Now, what about the case where nobody owns the spin or the lock? Well, in that case, then we're going to acquire it. So what we're going to do is we're going to set held to true. We'll set the owner to the current thread. Apologize for my handwriting. It's actually a little bit difficult to write on these things sometimes. And then finally, we will release our spin lock. And then we're going to return true. We got the lock. Okay. Now that we have try acquire, we can now use try acquire to actually solve, using no hold and wait, the deadlock from the previous code. So in function A, we are going to acquire lock A. All right, now you'll notice that I used acquire here, not try acquire. The reason why I can use acquire here is because I don't own any resources yet. And if you don't own any resources, it's okay to sleep. It's not okay to sleep or spin while you own something though. So the details come in the second acquire. So what we're going to do then is while try acquire returns false for A, we are going to, and this is where it gets a little weird, release A. And then we're going to acquire A. Now, you might be wondering, why did she just do that? Why did she release and reacquire? Well, what I want to happen is I can't spin and just keep trying to acquire the lock, because that's a form of waiting. And I am waiting to get B, or sorry, I guess this shouldn't be A, this should be B. It's too early in the morning. There we go. Oops. And even then, I've made a mistake. This should be A. So I tried to acquire B. Apologize for the confusion here. And then what I'm going to do is if I can't get B, I have to release A, because I can't own anything while I wait. Now, you can improve this a little bit by putting a yield in here to encourage a context switch. The reason why we release and acquire, though, is because what we're trying to do is we are trying to give an opportunity for somebody else to run here and change the state of lock B. And if I don't release A, then I would be waiting for B while owning something, and that is not permitted. Once, however, we break out of this while loop, then we can, of course, acquire B. And we can do whatever. And then in function B, we would do roughly the same. So we can't, and it doesn't actually matter what order we do things in here. So we acquire B because we don't own anything yet. And then we would do while we can't get A. We're going to release B. And then acquire B again. And of course, if you want to yield in between here to encourage a context switch, that would actually probably improve the performance just a teensy tiny bit. And then once we've broken out of this loop, we know we have both A and B, I've written acquire down here, and that's completely unnecessary. I am not having a good morning today. There we go. So the reason why you don't then have to acquire B afterwards is because try acquire, if you can get it, you will own it. So you don't need to do that afterwards. I apologize for the confusion there. It's too early in the morning. Okay, so that is using no hold and wait and try acquire. It's a little bit of work because let's suppose instead of 2 locks, now you have 3 locks. Well, if you've got 3 locks, then what you've kind of got to do is, acquire A, and then you've got to, while you can't get B, then you've got to, release A, acquire A, but then you have to try C. And then if you can't get C, you have to release A, and you have to release B. And then you have to go, I'm going to use a go-to here. I'm going to do it. Then you've got to go all the way back up here after you've tried to acquire A. That's awful. So this can actually get out of hand really quick. One of the other problems with no hold and wait is the fact that when you're going to have to do a lot of spinning. Now, you don't own anything while you spin, but you do a lot of spinning. All right. And it's at this point in the day where OneNote actually decides to crash finally. All right. So Is there an easier way to do it? And the answer is there is an alternate. I don't want to say it's easier, but there is an alternate way of doing this, and it's called resource ordering. And for resource ordering, you don't need try acquire. What we're simply going to do is we're going to assign every resource in the system a unique number, and then we ensure that when we are acquiring resources, we always do it in an increasing order. That's it. Solves the problem. So we have a question on Twitch here. Why can't we acquire one lock at a time? I'm not sure what you're referring to, but if you're referring to like doing a try acquire for B and then a try acquire for C and then coming back, like you have to come back. If you can't get C, you have to release A and B. And then after you've released A and B, you have to try to get A and B again so that you can then try to get C again. So what you end up doing is you've got to acquire A. You release A, you release B, you acquire A, and then you try to acquire B. If you can't get B, then you've got to release A. It's this lot of looping, and it gets really, really messy. So I'm not quite sure what you're asking. But if we don't do it in this specific way, then we have the risk of owning a lock while we are waiting. And if we own a lock while we are waiting and some other thread needs that lock, then we can run ourselves into this problem where we get into deadlock, and we don't want deadlock. Deadlock's very bad. So the last one, as I said, is resource ordering. Now I want to show you how much simpler the solution is for resource ordering. So let's scroll down. Well, let's just, you know what? Let's give a new page. It's just some nice black ink. All right, so what we're going to do now is I'm going to assume that every resource in the system has a unique number. So I'm going to say lock A is 1 and lock B is 2. It's pretty simple, right? And then in function A, what I'm going to do is I'm going to acquire it in the order A, B. And then I'm going to make sure that in function B, I also acquire it in the same order. So the problem that we had is the fact that those were in different orders in the two functions. When you always acquire resources in a strictly increasing manner, you are actually going to eliminate the deadlock problem. Because what happened before is we acquired A and then the other function acquired B, and then we tried to acquire B, so we fell asleep and then they fell asleep. But that doesn't happen here. So we acquire A, they try to acquire A. They are waiting on A. So then we run, we get B. Since they are waiting on A, they don't own B, which means we can then go into the body of our code, we can release everything, and then finally this will execute. So it does actually prevent deadlock, and it's easy-ish to implement. Now, you might be thinking, well, why doesn't everybody use this? Why would we have Banker's algorithm or anything else when this is so simple? And here's actually the problem. So let's say that I have a function that takes actually, I don't want to use numbered things. Let's say I have a function that takes 4 arguments. And people think, well, okay, I just need to acquire these locks. Let's say these are 4 locks. I'll just acquire them in the order A, B, C, D because that's the order of the arguments in the function header. But there's no guarantee that this is lock 1 and this is lock 2 and this is lock 3 and this is lock 4. That's not the case. We might call this function with locks 4, 3, 1, 2. And then the next time it gets called, it might be called with 3, 4, 2, 1. Do you see what I mean? So you don't actually know what the order of those resources is coming in. So what you're actually going to have to do inside of the function for resource ordering is before you can acquire, you need to sort them. So I've got to see, if A less than B less than C less than D, and then acquire A. And so you've literally got to sort. And as I'm sure you all know, sorting is not a free operation. If you have 1,000 different resources that you need to acquire, then I have to perform sort on those 1,000 resources before I can actually acquire them. That's not free. Now, I know there are lots of library functions out there that can make that a lot easier for you, but it's still not free. It's expensive. You should probably also ask, why are you trying to acquire 1,000 resources at once? All right, so those are our two primary ways that we do deadlock prevention. Now, I have another problem for you to look at, and I'm going to just introduce it today, and then we will look at the solution in review in our next episode. So let's go into here, and I want to look at the problem you're looking for is called queue transfer. So we have this problem where we have n queues of items, and they are shared queues. And I want to write a function called transfer, and I want to make this function take an item from the front of one queue and push it onto the back of another. So it's transferring an item from one queue to another. And it consumes two queues as arguments. Ugh, I just used racket terms. Sorry. So the thing you need to keep in mind is we want to make sure that transfer is atomic. That is, we want to make sure that we can have multiple transfers happening simultaneously without causing any race conditions. You can almost think of this as writing a transfer function for a bank, where a bank always wants to be transferring money from this account to another, but there may be many of these transfers happening at the same time. And we want to make sure that we don't end up with the wrong balance in any of those accounts. That's kind of the way you can think about it. So what we want you to do, and again, we'll look at this in our next episode, is we want you to use locks, just locks, to solve the synchronization problem and make sure that you have no deadlock. And the other thing is, see if you can maximize how many threads can run at a time. And for fun, see if you can minimize how many threads can run at a time. All right, so in our next episode, we will take up the solution to this. And then in our next episode, we're also going to be starting a new module, and that is the processes module. So we're going to be looking at all of the different things that we need to create processes, destroy processes, and how processes get isolated from the kernel. And hopefully, if we also have time in our next episode, we'll also give you a few more hints about the traffic synchronization problem. And I'll also be posting a few hints on Piazza as well, so make sure you watch carefully for them. So we will see you all on Thursday.
(1991) Helsinki, a 21-year-old student named Linus Torvalds writes a new computer operating system. He calls it Linux, then does something revolutionary. He gives it away, free, over the internet. The powers that be dismiss him as an eccentric, a freak, but everywhere coders and free thinkers embrace Linux, improve and refine it. Now the forces of openness have a powerful and unexpected new ally. It's a different kind of world. You need a different kind of software.